Good morning, everybody. This is Michael Valenzuela here, and I am more than excited to share with you a comprehensive review on the ResNet applications in medical imaging. Uh, that title may sound very technical and throwing all these jargon words in and doesn't make any sense right now, but by the end of the presentation, my goal is to make sure I break that title down bit by bit and that you understand everything about convolutional neural networks, what ResNet is within these CNNs, and how it affects the medical field, specifically medical imaging. So let's begin. Let's first define what ResNet is. And so ResNet is a deep learning technique that has revolutionized the field of computer vision with significant implications for medical diagnostics. The objective of the presentation is to explore three key areas where ResNet has been applied: lung disease identification, skin cancer classification, and brain pathology detection. By examining these diverse applications, we'll highlight the versatility and effectiveness of ResNet in addressing various challenges in medical imaging. ResNet, also known as residual networks, is a deep learning architecture that was introduced back in 2015 when I was 14. It addresses the challenge of training very deep neural networks by using a key innovation called skip connections. And these skip connections allow the networks to learn residual functions, which mitigates the vanishing gradient problem and enables the training of networks with hundreds or even thousands of layers. Now, diving deeper into the ResNet architecture, as you can see on the picture on the right of the PowerPoint slide, ResNet is composed of a series of residual blocks, each containing two main paths: the main path and the skip connection. The main path consists of a series of convolutional layers, batch normalization layers, and activation functions, as we see in the picture, ReLU, called ReLU. Last but not least, the skip connection, also known as a shortcut, this path bypasses the main path or skips over the main path, allowing the input to be directly added to the output of the main path. As we see here, the sum of block input and convolutional layer output is the skip path, and it just skips right through the main path. So this innovative approach of using skip connections is a key reason why ResNet is so effective in training deep, keyword deep, networks. It allows for better gradient flow during the backpropagation process, and it encourages the reuse of features across layers, leading to more efficient learning. So let's begin by exploring the application of ResNet with the lung disease identification using chest X-ray or CXR images. My reference, Hassana and their team conducted a comprehensive review of ResNet architectures in this domain utilizing the chest X-ray 14 dataset. The dataset itself contains 112,000 frontal view chest X-ray images and about 31,000 unique patients with 14 different thoracic disease labels. This presents a challenging multi-label classification task, but ResNet models demonstrated impressive performance. The researchers, like Hassana and their team, implemented a various network architectures, including ResNet 50, ResNet 101, ResNet 50, 152, and compare the results to other popular CNN models like the DenseNet and the Inception's version 3. The ResNet 50 model achieved an average AUC ROC of 0.841 or 84% across all 14 classes, outperforming the other architectures. This suggests that ResNet is a highly effective tool for automating and improving the accuracy of lung disease detection in medical imaging. And for those who don't know or need a refresher, the AUC represents the probability that the model, if given a random chosen positive or negative example, will rank the positive higher than the negative. In other words, it's essentially the performance. It's the measure of performance of the model. And so anything greater than 75% is pretty good. And in this case, the Hasana and the researchers got 84%, which is out of this world. Next, let's explore the application of ResNet in skincare classification. Skin cancer is one of the most common types of cancer, and early detection is crucial for effective treatment. Rodak and Nagajaran conducted a study on the use of ResNet for this task, focusing on the ISIC 2017 dataset. This dataset consists of 2,000 skin lesion images, including 374 melanoma, 254 seborrheic keratosis, and 1,372 nevus samples. The researchers included a ResNet architecture, and explored the use of data augmentation techniques to improve the model's performance. The ResNet models achieved an overall accuracy of 77% on the validation set. The researchers noted that the use of data augmentation, such as rotation and flipping, helped improve the model's generalization. This demonstrates the effectiveness of ResNet in addressing the challenging task of distinguishing between different types of skin lesions, which is crucial for early cancer detections. And finally, with our last example, brain pathology detection. This represents a significant advancement in neuroimaging analysis, offering potential improvements in the diagnosis and treatment of various neurological disorders. Chow and their team explored the use of ResNet combined with randomized neural networks, or RNNs, for this task. They utilized a dataset of 200 T1 weighted MRI brain images, equally divided between healthy controls and patients with pathological brain conditions. The researchers' novel approach improved pre-processing the MRI images, extracting features using a pre-trained ResNet AT model, and then applying the RNN for final classification. This combined model achieved an overall accuracy of 95.5% in distinguishing between healthy and pathological brain images, demonstrating excellent performance in detecting neurological abnormalities. And so what happened here in this research was they used ResNet, which is a CNN, and they combined it with a randomized neural network, an RNN, for this task. And when you do that, you get an incredible number like 95%. And now you're probably wondering, well, how come? Why couldn't I just use a CNN or the ResNet, an example, and have a higher number, expect a high number like that? And I'll tell you why. And so when you combine CNN like ResNet with a randomized neural network, it helps enhance the model's ability to understand both spatial patterns from CNN and more complex relationships in the data from the RNN. In this example, ResNet processes the MRI images by recognizing patterns related to brain structure, while the RNN helps capture more subtle patterns or irregularities that may indicate pathological conditions. When combined together, they can more accurately identify diseases, which is why they achieved such a high accuracy of 95%. The CNN focuses on visual features, and the RNN adds a layer of depth by making connections that aren't purely image-based. And so this combination allows for a more holistic analysis of the brain images. I hope that made sense. Moving on. As ResNet continues to demonstrate its effectiveness in medical image analysis, several promising directions for future research and development emerge. One area of focus is the potential improvement of ResNet architecture itself, such as developing adaptive versions that can dynamically adjust their depth based on the complexity of the input data. Incorporating attention mechanisms into ResNet is another avenue that could help the model focus on the most relevant features in medical images, potentially enhancing diagnostic accuracy. Additionally, there is growing interest in the integration of multimodal data, where ResNet-based models could combine information from medical imaging, patient history, and other clinical data sources to provide more comprehensive diagnosis and prognosis. Addressing ethical and regulatory considerations, such as ensuring fairness and transparency in ResNet-based medical tools, will also be an important area of focus as these technologies become more widely adopted in healthcare settings. In conclusion, the application of ResNet in medical image analysis has led to significant advances in areas such as lung cancer identification, skin cancer classification, and brain pathology detection. As the field continues to evolve, we can expect to see even more impressive applications of this powerful deep learning architecture, ultimately contributing to improved patient care and outcomes. And finally, questions. And so what I've done was, after completing my report and sending it off to the professor, I also ended up sending it to friends who were in the medical field and to friends who were not technical, not medical fields. And I told them to come up with questions that they may have. And these were some of the questions that someone with zero prior experience of either data science or medical field or just data science in general as a whole came up with. And so the first question was from a PA who said, what is ResNet and how does that relate to CNNs? And so she understood all the medical terms and how data science plays a big role in data and image processing, but she didn't understand the actual technicalities of distinguishing the difference between ResNet and CNN. And so what I told her was, CNN, or convolutional neural network, is actually a model used to recognize patterns in images. And ResNet, or residual network, is a type of deep learning architecture that's really good at solving computer vision tasks, like analyzing images in medical research, which is a kind of convolutional neural network. And so the CNN is the model itself, and the ResNet is the architecture within the model that makes it really good at understanding either high numbers of data sets within the data set itself, data points within the data set itself, or a very diverse amount of classifications, which is why it's so much faster than most other CNN or other CNN models, because it has the ability of the skip connection, which makes it much faster when the data becomes too big. And that's kind of the point of my presentation, which is separating ResNet in particular, the architecture, separating it away from other CNNs. And so moving on to the last question, can you explain to me convolutional neural networks like a 5-year-old? I kind of told them that a convolutional neural network is basically a robot that takes pictures, and it's kind of tasked to distinguish between a cat or a dog. And what it does is it takes a picture and it breaks it into little pieces like a puzzle, and it tries to solve it. And once it's solved, it says it's a cat, it's a dog. It classifies it. And that's kind of what data science or convolutional neural network really is. And so if you have any other questions, you can always email me back, or write it right here in the, what's it called? This is the Canvas. You can write it here in Canvas, or you can email me, and I will list my email below. Thank you so much for listening. I know it is 15 minutes now. So peace out. And that's all, folks. Have a good day, everybody. Thank you for listening.